Burning the bridge that keeps us. I'm here and I'm feeling fearless. Exaggerated, that's what you assume. The story's over now, I must conclude. I am conflicted, watching where I step still. Hanging in the balance, not the life I want to live. I want to take it all, standing tall. Fear I weighed the person you are.
Hey folks, how's everybody doing today? Happy Wednesday, hope you're doing well. Right, oh, it's an ad. Okay, so we can just mute that ad, let that ad run in the background. That ought to work. Cool. Alright, so we are here in week 5. Holy cow, this is the 1/3 of the way through a week. So we are flying through this semester. My apologies, I did not have Project 1 graded yet. I made a mistake, and the 4 classes that I'm teaching all had a project to do last week. Or no, I guess 3 of them. So I have 75 projects that I've been working through, or so. So I apologize, I'll be finishing those up this week for you folks. So you get your scores there on Project 1. And then we'll just keep on moving through. So only one chapter in the main chapter here, just chapter 7, and then these interludes about generics and exceptions. You know, we've pretty much done generics already. We'll take a quick look at that again, and then we'll talk about exceptions, which are fantastic. So this is the correct way for code to communicate. So it probably won't be super long tonight. Oh, sure. Yeah, Mizuki. So everything is timestamped in GitHub. So go ahead. D2L will flag it as late, but that's fine. If D2L flags it as late, then I go and look at your GitHub suspiciously. But I'll take a look and see some timestamps there. It should be fine. Awesome. So we're back to music. Finish those ads on mute. That's fantastic. You can just mute ads. All right. So that's the plan for tonight. Next project then will involve some recursion and probably not sorting. That's, you know, what you just call sorts. They're not all that interesting. But we'll work on some recursion stuff for project 3. Okay? So questions about project 2 before we get too far into this here? Any thoughts, questions, concerns? Again, questions are definitely encouraged, especially in, in the Discord, because just like we were in class in person, you ask a question there in the Discord, and everyone else gets to see it along with the answer. Appreciate. I'm not really sure. We'll see how long it goes, but I don't expect it to take. We probably won't be past 8 o'clock. Is the plan. So recursion's a decent sized topic, but then we've basically talked about it, generics already, and exceptions. They don't take. It's maybe 20 minutes of talking about for exceptions. So I expect that to go relatively quick. Okay, so again, we're doing this war simulator, and we want to count how many turns it takes to finish a game of war. And we're going to do that for 1 deck through 10 decks, running the game 100 times each, to see if we can find some kind of relationship between the number of turns and the number of decks, right? You might expect it to be linear, maybe you think it'll be more exponential. We'll find out, right? I don't think it's going to be logarithmic, right, where you get one of those flattening curves. But that's honestly, that's just a thought. So we can actually simulate it here to find out, which is fun. Is a turn the same as amount of cards played? No, so not the number of cards played. So like 1 turn is both people play a card. So maybe half the number of cards played, ray beams, if you want to count it that way. But then really a war, you're burning a couple more cards, but that only really counts as 1 turn. If you want to count the war part as a second turn, that's fine, but it's going to burn, 4 cards instead of just 1 each. So it might be a little bit tricky to count it that way. Or if you just want to say the war is part of the exact same turn, that's perfectly fine too. I'm not too concerned about how you count those, as long as you're doing it consistently. Okay, and then we got a rubric here for 15 points. Right, the comparable T. So, it's comparable of type card. So the T there, it's not, card is not a generic here, but like your comparable of type card, if that makes sense. So let me pull up my GitHub here. So I think I gave you some of this, didn't I? For project 2, did I give you anything about that? Give you card? No, I didn't give you card. Okay. So that comparable then, do I have comparable? Excuse me. You don't have comparable? I thought we had something that was comparable in here. Stack. That's what I thought. Thank you. In the regular stacks? You didn't do anything comparable here. Stack interface. Now this one's not comparable. This is just stack of type T. So this is saying this generic type. You can make a stack of any particular type. Whatever type you declare it here, it will be that type for all of these T's here. Where comparable is a little bit different. So the idea with comparable, let me start a new project here. So it's recursion. Oops. I'm typing in the wrong place. Want the project first. Maybe the quiz is first. I'm not sure. 2353. There we go. Make sure that goes in the GitHub repo. All right. So if you're going to write a class that implements comparable here, let's add a class, and sure, we'll just make this what a rectangle. Why not? Oh, that's right. Yes, we had rectangle. Okay, so we got a rectangle in inheritance and polymorphism, right? Let me just open up that project. That might be... No, that's fine. We'll just write it here. Okay, so we're going to have a public class rectangle. It'll have a private int for length and a private int for width. Okay, and then we want to... What? I can remove it. Sure, that's nice. I want to insert some code. Let's make a constructor. Sure, let's take length and width in our constructor. We'll add some sets and some gets. You know, let's just do get. So like once you get the size, we'll just leave it there. So no sets. So set in the constructor and then leave them alone for gets. And then we'll have a get area. Again, get area, which returns length times width. Okay. Cool. So now if we want to be able to compare rectangles, one rectangle to another, we can say, hey, we want to implements the comparable of type rectangle. This says, hey, I can compare myself with another rectangle. So it's not a T here, but comparable is a generic. So the interface is comparable with T, and you say, hey, I want to be comparable of rectangle. So I can compare myself to another rectangle. And then NetBeans is going to say, no, you don't. And we'll say, yes, we do. You implement this compare to method that overrides the compare to, or implements this compare to from the interface. It says, well, how do we compare our rectangle to the other rectangle? And what comparable needs, you'll notice it's an int value here. So we've used compare to before. Right? If you were, I think with strings, you probably did compare to with strings, maybe not. What would we have done that with? Maybe it's just strings, right? You get a 1, or you get a positive number if you're greater, you get a negative number if you're less than, and you get 0 if you're equivalent or equals to. Okay, so in our case, we're just going to return getArea minus o.getArea. Because the other rectangle here, I'll call that other. I prefer other to o. So how do I compare myself to the other? Well, let me check my area minus their area. If my area is larger, this will be a positive number. And positive means I'm larger. If my area is less than, then this will be a negative number. And negative means I'm smaller. And if we have the same area, then we're equivalent. So compare to doesn't have to be equals, you could be equivalent, right? So maybe we have 2 different rectangles with the same area, right? Definitely possible to have the same area with 2 different rectangles, but right, maybe we'll say we're equivalent here when we compare. So that's the comparable interface. Sorry, I didn't show you that before. I thought we had talked about that, but if we hadn't, now you have it. Okay, so our comparable interface, right? The card class has enums for face and suit. Our deck class has various numbers of decks, right? And can deal cards to the player. The player class has a stack of cards and an array list for their win pile. You can add cards to the stack from the deck or the win pile. Right, today when we're dealing cards out for a new hand, right, we should be able to, the player should have a public method that you can call that will add a card to their stack. You can use that method whether or not we're dealing cards or whether or not they're taking their win pile and reshuffling it back in, essentially. The player class when the stack is empty, shuffle the win pile, put it back into the stack, right, actually do this thing up here. The simulator runs 100 times, counting the number of turns until someone wins, averages the number of turns, and we run it for various deck sizes 1 to 10. Okay. So this card class is not actually worth a whole lot here, and if you're taking more than one of my classes, particularly the object-oriented programming in Java, you probably have seen the card class. So I'll save you folks some searching, and you can go out and find it in my other course repo here. So that's 2151 for the summer. A deck should start as all 52 cards, right? You have hearts, spades, clubs, and diamonds, and then you get 13 cards in each of those. You get 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, ace. So there's 13 faces and 4 suits. So we're doing a little Hold'em project here for Java 2, and then we have a card class. If you want to use this one, just cite the source, and look, it's even comparable of type card, because sure. Oh, that's okay, Mizuki. Just reference this, right? Leave a comment saying where you got it from, and we're cool. Because I know at least one person is in both classes, so if they have access to that, you might as well too. I'll save you that little bit of searching. Okay? So there's some free points on your project. And I'm only going to feel a little bit bad about it, because it's not much. Hey, Professor Burp, how you doing? I wasn't calling you out by name or anything. Okay, so don't have to reinvent shuffling. You can use collection shuffle. And you can shuffle an array list pretty nicely. We're just going to see if we can calculate how many times it works. And again, this player class, right, will have their own stack of cards that they use, that they play from. And the idea with the stack, right, you put something on top, you take it off the top. I sure could copy and paste the link. I sure could. Why not? You know what, I'll even put it in the Discord here, because that's... Oh, I'm not even logged into Discord. I should log into Discord. Would someone else post it in the Discord for me? And just leave a reminder to cite your source, please, for a card, and then I won't feel so bad. Okay? Other thoughts, questions, concerns about this project? Again, due next week by 6 p.m. So about 6 p.m. or so, or after my music's done, the intro music, I'll go over a solution to this. And that's what we'll do first next week when we talk about sorting. Okay? Okay, we'll just kind of keep that flow of things. We'll have a project every 2 weeks till we get to the midterm, and then we'll pick up the final project from there. Excuse me. Whew. Put my phone here on silent. Oh, thank you so much, Professor Burp. Yeah, I get Discord alerts occasionally. Alright, awesome. Beard Brigade, I want to buy follows. How can I do that? Oops, I clicked the ban button. Yeah, thanks. Yeah, I should make some of you folks mods so you can ban people for me. There we go. Yep. Let's make more money for that student scholarship fund over at the U of M Dearborn, where I'm both a lecturer and a student. You have to like in chat you can mod them. You have to have that sword. All right, so we're going to talk about recursion first, which is one of my favorite topics. Recursion is so much fun. It's really cool. You can ban a certain couple words. Oh, that's cool. So like have a bunch of words auto-modded, like by followers. But then it's unfortunate if you say that by mistake, right? Let's see, 2353. Yes, yep, as long as you cite your source, you and I are cool. Just leave it as a comment at the top, like, hey, I got it from here. We're good. Rectangle with parable of type rectangle. Okay, commit and push. The manual review thing? Yes, it'll automod and hold some things for me. Like if you start swearing, I think it automods you. I took like mostly the default settings, so I never really put a whole lot of time in any of the automod stuff. I figured anybody who's actually bored enough to come and watch, then they're probably fine. Thankfully, haven't had to deal too much with trolls. Hey, very cool. I'm glad Twitch recommended it. Thanks for coming on by. Alright, so we're going to talk about recursion. So the basic idea with recursion is you have a method that calls itself. So we're going to write a method here. Public void countdown is one of these silly fun ones here. It takes an int number. And the idea with recursion is that the method will end up calling itself as part of this process. And the idea is that you're going to take a big problem and you're going to break it down into a smaller piece and a smaller piece and a smaller piece and a smaller piece until you can actually solve it. So the idea is you have a base case that says, I can solve this problem. Right? I'm done. I don't need to recurse anymore. Okay? I don't need any more recursion. I'm done. I know what the answer is. So in our case, we're going to say, hey, if number is equal to 0, print out blast off. Okay, that's our base case. If we hit 0, we're done. If we're not at 0, we're going to print out the number, and then we're going to call countdown again, and we're going to get closer to our base case. We're going to get number minus minus. So if you call number and you give it a number, if it's not 0, then it's going to print out the number, and it's going to recurse with approaching the base case, trying to get one closer, one closer, one closer, one closer here. Right, so I can call countdown. Oops, countdown, and let's give it like 10. And I should get 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Oops, that's got to be static. There we go. Yep, it won't build if that's not static. Sorry. Now it'll auto run. Yes, so, uh-oh. Uh-oh. We broke it. What's happening? What did we do wrong, folks? You remember? This number minus minus. Right? Yes, we could do this. That's ugly. We do it this way? Well, that didn't go quite right either. Didn't stop. Blast off. And then it just kept on going. This probably should be in an else block. What do you think, folks? Should that be an else block? That probably makes a little bit more sense. Now it ought to stop. There we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Blast off. Okay, so the method calls itself, and calls itself, and calls itself, and calls itself, until we reach this base case. Now, if you're thinking, yeah, I could give it like -10, and we're going to be in essentially an infinite loop. Yes, you're right, but it's not actually an infinite loop. It should... Yep, here we go. It dies. Look at that, it crashed. Wow. So the stack trace here is really fun. Because it is... Everything is calling countdown, calling countdown, calling countdown, calling countdown, calling countdown, calling countdown. Over and over and over and over and over and over again. This is crazy. So let me put a breakpoint in right here at 11, and we're going to run it in debug mode. We're going to take a look at debug mode and see what we can find. And we're going to see... Maybe not it'll submit the breakpoint. What? Oh, it never hit, sorry. There we go. Actually put it back to 10. Yes, a loop would be easier just for counting down. This is just a basic example here. So what you'll see over here, in this far left here, this is the stack. This is the call stack. Right? So the first thing that happened is my program started here at main at line 6. Then it got to countdown at line 14, and line 14 called countdown again, and it called countdown again, and it called countdown again, and it called countdown again. So I can pop into each one of these here, and I'll see, if you double click it, it loads it up here, what the value is of number. Right? So the current value of number is 9, this first call, and then in this stack it's 8, and this one it's 7, 6, right? 5, 2, 1, 1, 0. And now we're at countdown of line 11, where we paused. So when you tell Java to go to a method, when you call a method, right, it's actually keeping all of those calls on the call stack. And this is why we talk about stacks first, because you have to kind of understand what a stack is. Excuse me. Okay, so you get main, and you start main line whatever, right? Line whatever here. If main calls a method, then it goes on the stack. It goes to the method at line whatever. If that method calls another method, it goes to that one. Method, method B maybe, method A, sure, at line whatever. Okay? Every time we call a method, Java needs to remember what was there. So these are called execution frames, essentially, and we'll keep them in memory along with all of the variables. Remember, if you declare variable, can't spell variable, sorry. If you declare a local variable, right, it's declared and exists within that method. Arguments here are essentially local variables. They exist within this curly brace block. It's a local variable to this method. Right? If we declared other variables inside of here, they'd be other local variables. Every time we go to a method, Java needs to remember what the local variables were where we left off, so that it knows when it's done, okay, let's just keep on going. So if I step here, right, we print out blast off, and then we're going to go back to the previous call here at line 14. Oh, I stepped over, sorry, I wanted the wrong step. It would have resolved each one, where we went back to line 14, countdown's done. Back to line 14, countdown's done. Back to line 14, countdown's done. So the method calls itself. So it's probably better here then to say, hey, if the number is less than 0, maybe do nothing? Or if it's less than or equal to 0, to say blast off? Because that way we can't say -10, and we won't run into these silly infinite loops here. Right? If we just say -10, we just blast off, because there was no countdown. Yeah, so this one is very simple. This is essentially a loop, right? And it's actually better as a loop because you don't have any of that overhead of those stack frames, those execution frames, where it has to remember what the value of number was for every call. So if we wanted to like count down 1,000 of them here, right? Java has to remember 1,000 numbers in the execution frames in this call stack. Oh, I didn't run into debug mode, sorry. But it's got 1,000 of those in memory. If we do it 10,000 times, it has to hold 10,000 numbers in memory. It'll blast off, but eventually, let's do like 100,000. And let's run it in debug mode here. I think I can probably show you, see if I can find my Java process. Can you find Java? Come on, let's check details. Java, no. Ooh, it already crashed already, oops. My goodness, we broke it. Okay, we did too many. That was not good. I think it broke. Wow. That's running super slow now. Can we see Java? There we go. Oh, it finished. Maybe it just is dying at 100,000. Okay, so maybe 10,000. Was that enough then? You can see that Java process. Java's using 17K memory to do that. And let's put it back up here, see if we can catch it one more time here for fun. We can catch Java. Java's using 15, 19K, 21K, and it crashed. So you can see it's using more and more and more memory because it has to remember all those stack frames, right? Definitely it's better as a loop. Public static void, countdown, loop, int number is much better. And we just say for, or I don't know, while number is greater than 0. Let's print out. Oh my goodness. The number. And then we'll take number minus minus. And when it's done, we'll print blast off. Okay. The countdown loop is obviously much better. Yeah, there's like the Java virtual machine is in charge of that, and that's also going to depend on your computer, right? So my computer has up to 16 gig of memory or so, but it's already using a ton of it right now, so it only has so much to share at the moment, right? So the Java virtual machine does a lot of that, and yeah, you can configure it, which is pretty cool. Okay, so this is just a basic recursion as a loop. This is the same thing done. So anything that can be done recursively can be done as a loop. Right? So anything that we do with recursion can be done as a loop. The reason why recursion is awesome is because it's better at solving some sort of problem, and it's easier than trying to do it in this iterative approach. So in this case, no, it's not super interesting, right? And it doesn't look like, and sure, that's fine. But a more interesting problem that's better with recursion, right? That you might want to solve. Let's do this one here. Let's do a Sudoku Solver. So I'm a big fan of Sudoku. I like Sudoku puzzles. I will say we have an array. I guess we can just do an array. I guess a basic array is fine. So we'll do an int two-dimensional array. This is the board. Okay, right, so it has to track the board. And then what we want to do is we want to probably have a method, a constructor that accepts a board. And we'll say our board equals a new int array of size board dot length. Oh, sure, it's 9 by 9. I'm sorry. And technically, you could have other ones, but that's fine. This dot board, right? And then for int row index is 0. Row index is less than 9. Row index plus plus. We're going to do a quick little loop through each row and through each column. Right? So then for int column index is 0. Column index is less than 9. column index plus plus. We're going to take this board equals the board, this board at row index at column index equals the board you were given at row index at column index. Sure. This is a copy, right? We don't want to take my board equals their board because then I have two variables pointed to the same location in memory. That's a big no-no, right? So we want to do a copy. Again, there's lots of other ways to do copies too, but it's a good habit to get into, like learning how to do these quick copies. Array copy is nice and easy too, but this is, right, it's just looping through, doing something basic. Okay, so given a board, right, great. And now let's see, can we do a public string? Let's do an override for toString. Override toString. So how do we represent ourselves as a string? Well, we want to use string builder. Builder equals a new string builder. Okay, and then we want to make this look nice and pretty. We're going to say builder.append, and we want to add in the box, right, essentially. 2, 3, 4, 5, 6, 7, 8, 9. I'm going to build this nice little looking Sudoku box. Or maybe we do 3, there we go. 3, we'll do a bunch of pipes in there. Okay, and you know what, those might actually need more space. I don't know, we'll see. Yeah, we should do more, right? We can do all of them as pipes. No, that's not as fun. This will be fine. Okay, and then builder.append. We want to add in, oh, also a new line here, right? Ugh, sure. Plus a new line. We have to add in our own new lines. We can't do, no, yeah, append. All right, and then we'll add in the pipe, and then we'll add in our characters. Right, so maybe we do this as a string format. And then a digit, a pipe, digit, pipe, digit, pipe. Probably close, right? And then we need to give it the digits. Oh, goodness. Well, okay, so this.board at 0, at 0. It's going to be long. Oh, I need some commas here. That's why it's mad at me. Do some commas. Comma, 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 comma. Comma, not a period. Comma. 0. So row 0, 1, row 0, 2, row 0, 3, row 0, 4, row 0, 5. 6, 7, and 8. That should be the whole row there, right? And you know what? This is really obnoxious here. So I want to take all of this and refactor, and I want to extract or introduce a method. Oh, come on. That's fine. So we're going to add a little public, or no, this will be a private string get row string. And we're going to return, and you tell me the int row number or row index. How about that? So I'll do row index here of 0, 1, 2, 3, 4, 5, 6, 7, 8 and build you a nice pretty row. Okay, so we're just going to sub in all those digits here, plug them all in, right? So then I can append my get row string of 0 with a new line. Or, yeah, should we add in our, we should do our own new lines here, I guess, right? I don't know, we'll do the new lines here. Nah, here. So 0, 1, and 2. Right, and then throw another one of these out there. Ugh, okay, that's obnoxious here now. So let's do it again. So let's do private string get, I don't know, or get 3 rows. I don't know. Does that make sense? Int starting row index. That one. Sure. So we'll get the row string, get the row string, get the row string, get that one, and then we'll return builder.toString. So, but now I want the row index +1, and row index +2. Okay, so I'll start that, and then I'll get 3 rows, builder.append, get 3 rows starting at 0, get 3 rows starting at 3, and at 6. And then we can return builder.toString. Oh goodness, all this to get like somewhat of a pretty-ish looking board. I don't know, do we need to have better lines in between all of them? Maybe they all need to be in boxes. I don't know. Is that better if they're all in boxes? Like that? Did that make it look any prettier? It might. Okay, so then we don't even need... Let's just do... that. And a new line. And then that for each one of them. Sure, and we don't need the 3. Then we can just loop through. So for row index 0, row index is less than 9, row index plus, where's my plus key? I can't, oh my goodness. No! There we go. Builder append, get row string, given the row index. And then I need one last one of these here at the bottom, right? Oh, I need those all need their pipes here then, right? Builder.append, add in one more of those at the end. And then return builder.toString. Alright, so maybe that'll be pretty. Oh my goodness, all that work just to get a little board here. Sorry. We'll give it a countdown. Let's make a new int array, 2D array called the board. A new int array of 9 by 9. Then we need to go set up the board here, right? Whew. All right, so let's go find a Sudoku puzzle. Sudoku. Let's see if we can find one here. Okay. Sure, that looks like a nice one here. So let's see, can we translate that into my board? I bet we can. You know, we can do it this way, right? We can just say it equals int array. Right, we can do it this way with zeros, I guess. Oh, zeros are ugly, but that's fine. 0, 0, 0. Oh, so that's row. So can I shrink that down? I just unpop it. My unpin. There we go. 0, 0, 0, 7, 5, 0. Oh, where'd it go? There it is. 0, 0. There's the first row. And here, let's do all the other ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the last closing curly brace here. Okay. That's a 7, 0, 0, 0, 1, 0, 0, 0, 0, 0, 4. Right, so we're using zeros for, hey, Sinombre, welcome on board. we're seeing if we can make a Sudoku solver here using recursion. 2, okay, and then 1, 3, 9, 0, 0, 0, 8. All right, those zeros are ugly, and I'm feeling bad now. So that's okay. 3, 7, 8, 6, 0, 4, 0, 0, 7, 1, 4. I'm sorry, if you're not familiar with Sudoku, the idea is you want to get all 9 numbers in every row, every column, and every 3x3 grid with no repeats. Yeah, sure is. Exclam course there if you're interested for more information. 5, 3, 0, and 1. 0, 0. That's a 6 and a 4. All right, so when we're done, we'll have all of our numbers from 1 to 9 in every column, in every row, and then in every 3x3 grid. We'll have them here. That's the goal. Okay, so let's try and make a new Sudoku solver then. Let's see, I think I got that there. So Sudoku solver, Sudoku, I don't know, Sudoku equals a new Sudoku given the board. And we'll just see if we can print it. All right, just want it to be pretty. As you'll have a bunch of zeros, so it might be a little bit ugly, but that's okay. We'll fix that part after. Objects. Dock. There we go. Oh, I didn't dock it. It's fine. No. Oh, goodness. Stop being obnoxious. All right, there we go. I think now we're back to normal. No, heckling is fine. Heckling is fine. All right, so what did we do wrong here? We took out too many curly braces. Is that looking better? I think that's looking better. We'll see if that runs. There, all right. So all the zeros for all those places. We get our numbers back out. I think that's okay so far. Maybe not the prettiest Sudoku board, but sure. That ought to do it. All right, we put them all in a box. Okay? So, what we're going to do here for solving Sudoku, we're going to use recursion, but we're going to use something that's called backtracking. And the idea is that we want to try something, and if our base case is we solved the puzzle, we win, great. If the base case is I can't do anything else, oops, and I'm not done, right? Then we need to backtrack, we need to undo. So the idea here is we're going to take this puzzle and we're going to say, okay, give me the first open square. That'll be this one here. I'm going to say, okay, can I put a 1 in? Yeah, let's put a 1 in. If you can put a 1 in, great. Okay, put the 1 in. Go to the next open square. All right, that's this one here. Can I put a 1 in? No. Can I put a 2 in? Sure, looks like I can put a 2 in. Put a 2 in. Go to the next one. Okay, now I'm here. Can I put a 1 in? No. Can I put a 2 in? No. Can I put a 3 in? Sure, looks like I can put a 3 in. I put a 3 in. Go to the next open square. I'm here. Can I put a 1 in? No. 2, no. 3, no. 4. Sure, I can put a 4. Put a 4 in. Go to the next open square. 1, 2, 3, 4. No. 5, no. 6. Yeah, put in the 6. Great. Go to the next open square. Right over here. 1, 2, 3, 4, 5, 6, 7 are a no. 8 looks like a yes. Sure, put in an 8. Go to the next open square. 1, 2, 3, 4, 5, 6, 7, 8, no. 9 is also a no. So, oops, we couldn't do that. That was bad. Go back and undo that step here. Right, backtrack, undo it, and then, okay, we tried 8. How about 9? All right, put a 9 in. Great. Go to the next square. Nope, can't put any of those in. 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't fit. So go back. Oop, 9 was no good. Undo that one. Go back here. All right, well, now I'm back here. I put a 6 in. 6 was no good. How about a 7? Nope, no 7, no 8, no 9. Nope, this was no good. Go back here. Undo the 4. Now try a 5. Can't be a 5. Let's try a 6 here. So it's going back, all the way on back. Right? Trying to undo itself here as we go. So to solve Sudoku then, right, our two base cases are we can't put any more pieces down, and we have to undo, or we're solved, we win. So let's write a private Boolean is solved. And we can figure out if we're solved whether or not pretty quickly here. So I'm going to say for int row in board, and then for int, I don't know what, column, I guess it's not really column, but sure, or number in row. If the number is 0, return false. We're not solved. No, the Sudoku Solver is pretty quick, and it goes pretty well, and it shows a lot of these interesting concepts. So if we have a 0 in the board, right, we're not solved. It's no good. Right? If we get through all of this and we haven't found a 0, we must be solved. True. Right? Life is good. We solved the puzzle. Okay? Because there's no zeros left. Okay? So what we're going to do then, our public method here, public void solve, is going to attempt to solve the puzzle. This will be our recursive solution here. So what we want to do, right? Let's see if we can get our steps down here. Where'd my pen go? Right here. Right, so we have our board. Right, 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Sure, that's probably close. Right? And we have a bunch of numbers in here, right? We had a 7 and a 2 and a 5. I don't know. They don't actually matter right now. 3, 2, 1. Something like that. Right? We had a bunch of numbers. Oh, shoot. I lost the internet. What's going on, friends? What is going on? Am I back? We might be back. Sorry, folks. Where's my phone freaking out? All right, still here? Yeah, sorry about that. I don't know what's up with that. Anyway, so we're gonna just try it and see. So what we need to do is we need to get the first available spot. That's the first 0, right? So we need to find the next available spot, and that'll be our row and column index. Right? So we need a little helper method for private. Sure, int. Ugh, that's ugly. I really want 2 ints. That's unfortunate. We'll do an int array. Why not? That's fine. Int array, get first 0. Right, so we're going to loop through again. But now I can't use these for loops because I need the indexes to return. I'm going to say for int row index and int column index. There we go. Yep, inside of here. If board at row index at column index is equal to a 0, return row new array int array of row index and column index. Okay. If we go through all of that and we haven't returned anything yet, well, it was no good. I'm just going to return, I don't know, like new int array of 0, 0. I'm not, how about -1? -1? Something bad, like this should not happen. Right? We shouldn't get the first 0, right? Otherwise. What we want to do, when we recursively call solve, we're going to check if is solved, and really we want the not. So if we're not solved, if there's still a 0 out there, right? Great. Oh, actually, we could have used this one too, but that's okay. They do sort of the same thing, but this one returns a -1, -1. That's okay. So if it's not solved, then I'll have a int array first 0 is get first 0. And an int row index is equal to the first 0 first index, and the int column index is equal to the first 0, column 1. Because we're returning these two items, row and column index here. So if we're not solved, go get the first 0. Great. Now that we have the first 0, I'm going to start trying to put numbers in. Right? The idea was I can put a number in if the row is clear, if the column is clear, the row is clear, and the 3 by 3 is clear of that number. So that part's a little bit tricky, but that's okay. We'll break it down into steps. So we're going to say now for int numbers 1, number is less than or equal to 9, I don't know, or less than 10, either way you want, it's fine. Number plus plus. We're going to say if can place number, and we need to tell it, hey, where are we trying to place it? We're going to try and place the number at the row index, at the column index. If we can, right, then we're going to place the number. We'll say self.board, or the board, right? Board at row index at column index is equal to the number, right? Put the number in. If we put the number in, great, now we're going to call solve. We're going to recurse. Okay, so this can place number is a little bit tricky here, so we need another little helper method. So private boolean can place number, given a number, sorry, an int number, an int row index, and an int column index. Okay, so the row index first is easy. So we're going to return can place number at row, given the int number and the int row index. Right, you can place it in the row, and can place the number at column, given the column index, and can place number in 3 by 3, given the number, the row index, and the column index. Right, we're just taking these big problems and breaking them down step by step by step into smaller and smaller and smaller problems, right? Like the big problem is, how do you know if you can place a number there? Right? Well, sure, okay, well, can you place a number in the row? Can you place a number in the column? And can you place a number in the 3 by 3 grid? So we're just going to break it down, right? Step by step by step. So private boolean can place number at row, given an int number and an int row index. Right, we're going to loop through. So for int number in board at row index. This is number, I don't know what, current number? I don't know, current number? Why not? So if the number is equal to the current number, return false. If we make it through the whole row, we haven't returned false, it doesn't exist in that row, we're safe to put it in that row. Right, so take a look at that row in the board, right, grab every number out of it, and check, is that number existing? Is it current? Is it already there? Right, so for this row, if I try and put in a 7, it's going to say no, because there's already a 7 in this row. Okay? Same idea with the column. So can place number at column. Goodness, that formatted terribly. Oh, I don't have to tell it ints over here. I'm so sad. So confused. I'm sorry, folks. One of those days. You don't have to redeclare it. It's only when you're writing the method. I'm sorry. Ugh, why did that get so ugly? And, ugh. Okay, anyway, so the column, and this is now the column index here. We'll fix that up in just a second. Now, we don't want to loop through every board at row index. What we want to do is we want to loop through for every row in board. If the number is equal to, or we'll do if the row at the column index is equal to the number, return false. Right? So I'm going to look at every column. So if you say, hey, let's check column 3 here, index 3, I'm going to look at every, where did it go again? Put it back. So column 3, right, this is 0, 1, 2, 3. It's going to look at every row at index 3. Does it match? 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 If it finds a match, false. You can't put it in that column. Okay? And then this last one here, this one's a little bit trickier. Boolean number, int row index, int column index. Now, this one takes a little bit of thinking here, but it turns out I've done this before, go figure. And the logic here makes a little bit of sense if you take a second to puzzle it out. Okay, maybe that'll be a little prettier there. So for the 3x3s, right, in this little Sudoku board, you have 0, 1, 2. You have, that's one grouping. You have 3, 4, 5 as another grouping, and then you have 6, 7, 8 as another grouping. Okay, so if your row is either 0, 1, or 2, you need to check those 3. If it's 3, 4, or 5, you need to check those 3. If it's 6, 7, or 8, you need to check those 3. And if you do a little bit of arithmetic, if you say your row floor divided by 3, integer division by 3, will tell you how many whole number 3s you can count in there. 0, 1, and 2 will give you 0. 3, 4, and 5 will give you 1. 6, 7, and 8 will give you 2. That's your starting place. And you can do the same thing with the columns. Okay? So we're going to check. So we're going to get the int first row is row index divided by 3. And I want integer division here, right? I want it to drop all the decimal remainder. And I'll have a first column. Is my column index divided by 3. Okay? Now I'm going to loop. So I'm going to say for int, what do we want to check here? I don't know, row index check starts off as the first row. First row. And then the row index to check is less than the first row plus 3. Row index to check plus plus. How's that look? Right, so we're going to start with it floor divided, right, divided integer division by 3. Starts with the first row. As long as it's less than the first row plus 3, we want to keep on going. And again, we're going to do the same thing for column. So for int column index to check is the first column. Column index to check is less than the first column plus 3. Column index to check plus plus. Okay, and we'll check if the board at the row index to check, at the column index to check, is equal to the number, return false. If we've done all of that, and we haven't found it, we can return true. Right? Again, this is just some arithmetic, but I need to check a 3x3, and I need to start at either 0, 1, or 2. Same with columns, 0, 1, or 2. Then I'm going to check 3 columns, and I'm going to check 3 rows. Okay, so I can place the number if it doesn't exist in the row, doesn't exist in the column, and doesn't exist in the 3x3. So I'm going to try it. I recurse. Okay, so this is the way to start solving it, but we haven't done the backtracking part yet. Okay, so to backtrack, if we try solve and we got stuck, remember we said, hey, let's put a, where were we here? We're on this one, right? Yeah, so if we got to here and we couldn't put in an 8 or a 9, we had to come back. You have to undo that step. Right? You have to undo it because it was no good. So to undo it, right, we need to put it back to 0. So if we come back from solve, and if we're still not solved, I'm going to put this back to a 0. So I'm still checking because I want to make sure if I did solve it that I don't undo that again. Right? So if it's not solved, put it back to a 0. And then this loop will just keep on running. Okay, let's try a 9. Once we've tried all 9, it puts it back to a 0, right, because we're not solved, and then it's going to go back to the previous one. So let's try it. Let's see if we can solve it here. So we'll print out the board, we'll try Sudoku.solve, and then we'll print out the board again. See if it solves. Uh-oh. Does not appear to have solved it. Uh-oh. And let's do some other print lines here, just to give ourselves some space. No, that's the original board, isn't it? 7.5 didn't change. Did it not solve? Now I'm confused. Can place the number. Set it to the number. Call solve. It's not solved. Put it back to 0. Oh, let's try it in debug mode. I don't know. We'll find out. Put it in debug. Oh, debug this one here. Okay, so we're in our Sudoku board, right? We have our board here. This is a little two-dimensional list. So we should, we're not solved, so let's get our first 0 is at 0, 0, great. And then we're going to try the number. And say, hey, can we place the number? Okay, we can place the number. We'll put the number in. So now number is 1, so my board at row and column, right, 0, 0 is now a 1. We're going to recursively call solve. So we're back to solve. My board is still, now it has a 1 there. Right, got a first row and first column. Now it's at column 1. Great. Going to place a number. Oh, can't place a 1. Can I place a 2? Yeah, I can place a 2. So it places a 2, recurses. Keeps on going. I wonder if this one's got to be solvable, right? Let's see. We eventually want to get stuck here. Let's see. Where are we here? Maybe a 5. Nope. Can be a 6. It's a 6. It'll be a 7. Right, we placed an 8 on the board, and we're going to solve. All right, so now we should be stuck, right? Because this board here, our first row has 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 7, 5, 8, right? Just like this puzzle, and we shouldn't be able to put a 9 here. That's the goal. Keep on going then. And notice the call stack over here, right? So this is all the things Sudoku, right? These are all the calls we've made. So this was the first one, the second one, the third one, the fourth one, fifth one, sixth one, seventh one, on and on and on. We're calling, we're trying to put all the numbers in. 1 through 8, 1 through 9. We couldn't place 9. So that for loop is done, right? The whole method here is done. So we're going to go back in the call stack here to this one now, right? Great, so now we're here where number was 8. We just tried an 8. 8 was no good, so we're not solved. Let's put it back to a 0 and check the next one. Can we place a 9? Yeah, we can place a 9, so let's try placing a 9. All right, we'll go on back. Try that one again. All right, reset. That one was no good. Now we're going to place the 7. You know, let's do this. Let's print it out every time we recurse. Let's just let's print ourselves. Again, this is kind of ugly to be printing here. Two string. I don't know. Just print ourselves. You know, just 2 string. And then we'll print just another blank line too. Okay. Let's try that. See how far we get with it. We should have a bunch of prints here, but yeah, so this is every step of the way as we're trying to solve it, it's printing it out. See how far we get. All right, well, we got to 9. And we weren't able to place that last one. Couldn't be a 1. Did we not find a solution? Let's try this. Let's see. So if it is solved, then else, see if that'll print. Just for fun. Maybe we're finding a solution. We're just undoing it by mistake somehow. I just picked the first Sudoku I found. I don't actually know if it's solvable. I figured they all were, but maybe not. Nope, that one's not solvable. Huh. Let's try another one just for fun. I feel like this should work. See if we can find another Sudoku. Right? Sure. That one looks a little better. We'll try that one, okay? Let's squeeze that over here. All right, so I'm going to do all zeros to start, and I'll plug the numbers in. That might be easier. 1, 2, 3. This idea with the backtracking recursion, right, is that it's essentially a loop, but there's so many things that it's tracking for us. Yeah, solve it by hand first, for sure, but I might take a little longer. 7, 5, 8, 3, 2, 9, 7, 4, 4, 8, 3, 9, 8, 3, oops, 7. Okay, got those ones. 3, 9, 2, 4, 7, 1, 2, 6, 8, 3, 1, 8, 9, 2, 7, 5. Oh, did I do that wrong? 5. Right, so 1, 7, 5, 2, 9, 7, 8, 6, 1, 3, 8, 1, 2, 7, 4, 2, 9, 8, 3, 9, 7, 4, 2, 4, 8, 3, 9, 3, 8, 7. Okay, let's try that one here. Nope. All right, well, we did something wrong, then shoot. Because that one didn't solve either. All right, we got a bug somewhere. Let's say is solved. If we find a 0, it's not solved. Get the first 0. If it's a 0, return that, right? Yep, that should give me the first 0. Can place number, right? At the row. For number in the row. For column in the row. 3 by 3 check, right? First row plus 3. First column plus 3. I think that's fine. Can place. No, that should be good. We're anding together. Thought I had it. Solve. It's not solved. Reset. Take it out. All right, let's go back to this then. That's fun. Print every step of the way for a little while. You know what? Let's do this. Let's let me add another little helper method here. Have it int count zeros. So we'll have an int zeros, starts off at 0, and then we'll just do this little loop here. And if it's a 0, we'll take zeros plus plus. I'll return zeros. So then we can do a little bit smarter here. We can say, hey, if count zeros is maybe less than 5, maybe. So if we have less than 5 zeros left in the board, we'll print it out, see if we get any better without having to look at every single one of these here. See if we get any closer. Okay, no, we don't get any closer than that. Okay, so that's something's definitely wrong. How about less than 10 zeros? Oh, I'm doing something silly, I'm sure now. Still doesn't even get that close, okay? One of these must be off then. number in the row, that's the row. Number the column, that's the column. 3 by 3. Place the number, great. All right, let's keep going. We get less than 15 zeros. Nope. Oh goodness. All right, do I have to solve it by hand? Do I really have to solve one? This one looks like it should be solvable, right? Got all the 9s already? I don't know. It's interesting. All right, forget it. We'll just print them all. See where we start running into trouble, maybe. Ooh, that was quick. Did we ever get the first... Never even get the first column done? Should be able to get at least the first column done, right? 8, 1, 4, 2, 3. One, 2, 3, 4. Should be able to put a 5. Yeah, I should be able to put a 5 in there. Why didn't I put a 5 in there? Five should have been safe. All right, maybe I have something mixed up here then. So the row index, the column index, and the number. Number on the column index, number on the row index. Then place number, row index, column index. All right, we'll just run into debug one more time. Sorry, folks. All right, so let's do a bunch of stepping out till we get that filled in here. Okay, so we're at 4, 1, 2, 3, 6, 8, 9, 0, 7. And something didn't work, so we reset that one to a 0. Okay, sure. Step out. We had to reset that one. 3, 8. Okay, so what do we have here? 1, 2, 3, 4. So it should be a 5 here then, right? That we're going to try. See what number is here. Let's see. Number is 1, 2, 3, 4, 5. Let's step in. And let's see, can we place number 5 at row 0, column 7? So it should be fine for the row. Step in for the row. Checking all of these. If we get a 5, it's no good. All right, good for the row. And we'll step in. Let's check the column. Here's where we thought we might have had trouble, right? It wasn't putting a 5. So for row at column, if it is a 5, so what's on my board right now? So I need all of the column 7s. So column 7 is a 0. Column 7 is a 0. Column 7 is a 0. Column 7 is a 4. Column 7 is a 0. Column 7 is a 0. Column 7 is a 0. And column 7 is a 7. We should be okay, right? Let's see what it does. We're trying to put a 5 in here. Okay, so returning true. That's good. All right, now we'll check the placing the number in the 3 by 3. we're placing number 5, row 0, column 7. So first row should be 0, and first column should be 2. Oh, yep, that's the problem. That is the problem. So my place number of the 3 by 3 is wrong. So I got the correct grouping here, but I forgot to get back to the first correct number. So it's starting at column 2, not column 7. Oh my goodness, friends. So divided by 3, right? And then multiplied by 3. Right, because 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6. Sorry, folks. That ought to do it. There we go. I did have a bug there. Did have a bug. How sad. It's my fancy arithmetic. Alright, so let's close all that. Get rid of all those ones. Now it should solve. Look at that, we solved it! We solved Sudoku! Okay, so here's our solution. Let's give it a quick check. 812546937. Right, this column, 86. So we got a 1, we have a 2, we have a 3, we have a 4, we have a 5, we have a 6, we have a 7, we have an 8, and we have a 9. Cool. So this is backtracking recursion. This method is calling itself until we either get the base case of it is solved, right? If it is solved, we're done. There's no more recursion. Or the other case is that we can't do anything else, right? And we just need to undo. Because if we can't place a number, the whole thing just, that iteration stops, right? So as soon as we hit that dead end, it comes back and undoes. So this is the undo step, right? So if returns from the recursive call and isn't solved, undo. Right, that's the backtrack, is the undo. Yeah, so we took out all the other steps. So we can undo these prints here, and solve will just print itself here. Here we go, and there's our solved Sudoku. Rishi, you're too kind. All right, yeah, if you get rid of your little logic errors there with your clever arithmetic that ends up not being clever, right? Then it ought to solve. Just took a little bit of debugging, which is good practice, I promise you. Being able to debug your program and step through and see what's happening is super huge and well worth it to learn how to do that, because it happens all the time, right? Apparently we haven't done a good job of teaching you folks how to use the debugger. So that's also on the hit list of things to do. That was on purpose. Clearly it was on purpose because I wanted to show you how I use the debugger for solving problems. You mean in the solution? I just wanted to like have it look like a box. Maybe we didn't need that. Does that make it too ugly? I thought, yeah. So if we undo that, then we get rid of this. And we just do that in the top and bottom, maybe? Think that'd be better? Run. Does that look better? Oops, forgot a new line. Sudoku plus a new line. Does that look better? Guess we don't even need those other lines there, do we? That looks even, okay, sure. Let's get rid of those then. I don't like them. Get rid of them. Gone. Buttery smooth. You know, I kind of like those other ones, but that's okay. Top and bottom. It's fine. Cool. Or maybe if we did every third, like to divide those groups, I don't know. It's fine. It's fine. So this is backtracking recursion. So we could do this exact same thing iteratively. This solve method. Stretch. Thank you so much, Professor Perp. Definitely a stretch is in order. We could do it iteratively, right? This would be another loop, essentially, right? A loop inside of a loop, and we would try every one, but then undoing and going back is much harder, right? Because it's not just a loop. The idea is that we're going deeper and deeper and deeper, further and further and further, and then we need to be able to undo the step and undo the step and undo the step. So what the call stack is doing for us is it's like saving the state of things. So you can solve problems like this that are recursive by using a stack, and you keep the state in a stack, and then you can undo and get rid of and go back to that previous state. But in that case, you end up actually having like a lot of other things in memory if you need to be tracking your state that way. This way, because the board only exists once, right? It's a class level instance, or class level variable, an instance variable. We're operating on the board. We're not making copies of anything. The only thing each call in that stack is tracking is what is the current value of number in this loop. And at most, we have 80 of those, right? Which is not too bad. Like 80 integers, it's tiny, right? Because the board is only 9 by 9, and I know I'm going to have at least one number, right? And I guess we could start with a completely empty board and come up with the first solution. That might be fun, right? We could just come up with an empty board. And put this all back to zeros, right? We could do that. And just let the computer solve it for us, right? So at most, then we'd have 81 calls on the call stack. Actually, I'd like it better with numbers. I'm sorry. You know, you can play with it later if you want to put zeros in, but I like it with the numbers. Okay, so here's Sudoku, backtracking, recursion. So you can do a similar thing with all sorts of problems that can be solved recursively, right? By undoing. So let's try this, 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 let's undo. Let's try this, let's try this, let's try this, let's try this, let's undo. So backtracking is not always the fastest, but it's like a brute force way of trying to solve. Okay, so you could solve a maze with that same idea, right? So if we had some sort of maze to solve, right? Imagine, you know, here's your start, here's your end, and then we'll just put some grids in here. Right, the maze is going to be a little bit different to solve, but maybe we'll say, hey, if there's an X, it's a wall or something, and you can't go through walls, right? Sure, why not? I don't know. So with the maze, right, we're going to say, well, is it solved, right? My base case is it solved? Right? Did I get to the end? If I'm not at the end, how can I get recursively closer to it, right? You have to have a base case, and you have to have a way to recursively get closer to that base case. So with Sudoku, right, the base case was we don't have any zeros. To get closer to not having any zeros, we put a number in. Okay, so with the maze, right, we'll say, hey, what are the possible things we could do, right? We're not trying numbers 1 through 9. With a maze, you can go up, you can go down, you can go left, and you go right. Okay, so if we start here at start, right, we're at 0, 0. Okay, row 0, column 0. Can we go up? No, can't go up. Can we go down? Sure, let's go down. So now we're here. So now we're at 1, 0. Can we go up? No, we can't go up. Can we go down? Sure, let's go down. Now we're at 2, 0. Can we go up? No. Can we go down? Sure, we'll go down. Now we're at 3, 0. Can we go up? No. Can we go down? Sure, now we're at 4, 0. We're here. Can we go up? No. Can we go down? No. Can we go left? No. Can we go right? No. Oops, this was bad, right? Undo. 3, we tried up, we tried down, we can't go left, we can't go right. Undo. 2, 0, right? So these calls come off the call stack. Okay, so now we're at 2, 0. We tried up, we tried down, can't go left, let's go right. So now we're at 2, 1. Right, so imagine all these calls are on the call stack. So 0, 0, and then 1, 0, and then 2, 0. I'm going the wrong direction, I'm sorry. 0, 0, we did up, down, left, right. So we tried up, we did down. And then at 1, 0, we can't go up, we went down, still have left and right to try. At 2, 0, right, we did up, we did down, went we can't go left, and we tried right. Now we're at 2, 1. 2, 1 says, okay, up, down, left, right. You can't go up, can't go down, can't go left. Let's go right. So now we're at, 2, 2. Right? 2, 2. Let's go up. Up, down, left, right. All right, let's try up. So then we go to 1, 2. Up, down, left, right. Okay, let's go up. Now we're at 0, 2. Right, now we're here. Up, down, left, right. You can't go up, can't go down, you can't go left. Let's try right. So now we're at 0, 3. Right, we're here. Up, down, left, right. Can't go up, can't go down, can't go left. Let's go right. So we're at 0, 4. Up, down, left, right. Can't go up, can't go down, can't go left. I'm sorry, we can go down. Sorry. Up, down, left, right. Let's go down. So then we're at 1, 4. All right, we went down. Up, down, left, right. Up, down, left, right. Over and over and over. We just keep doing this. So all of these calls here are on the call stack. Right, for the maze solver. So you can solve a maze with backtracking recursion. All right, there's a really cool thing I want to show you. I'm not missing anything important here. Yep. Those are all fine. Yeah, here we go. So let's look at this 3D Tower of Hanoi. Solver. I think it's this website. Number of disks. 3 disks. Let's do more disks. Let's do 5 disks. So with 5 disks, the idea is this puzzle is called the Tower of Hanoi, and that you can't put a smaller disk on top of a larger disk. Otherwise, it'll get crushed. And you have to get all the disks from one pole to another pole. Okay? So this turns out to be a very easy to solve with recursion solution, and difficult to solve without it. So we have 3 poles here, and we have, let's just do like 3 disks for now. And we're going to get all 3 from here over to here. Well, I can't solve that problem, right? But the recursive, the how do I get closer to solving that is, well, I know how to move one disk, right? Moving one disk is really easy. Okay, so if I need to move all 3, well, let's get closer to that solution. Let's move just one disk. I'm sorry, let's move one less. I'm sorry, so if I want to move all 3, that's hard to do. How about instead of 3, let's move 2, and then I'll move them to the other place here, and then I'll move the 3rd disk over to here, and I'll move 2 from here back on top. Well, moving 2 is hard, right? So I'll move one disk from here to here. So I'll take this one disk, and I'll put it over here, right? Comes off the top. I'll move the 2nd disk, put it over here, and then put the one disk back on top. Okay, then I can move the 3rd disk back over to here, and then I can move these 2 disks back to there. Well, 2 is hard, so 1 is move 1 over here, move that one over here, and then move the 1 back on top. So it's this idea, the whole thing, this is not the one I wanted. There's a prettier one. I think it's this one. Yeah, this one is so cool. So we want to have 3 pegs, and let's do 5 disks. Nope, get solution, sorry. Nope, 3D, sorry. 3 disks, 3 pegs, no, 5 disks. No, we'll just do 3 disks, 3 pegs. Okay, so it's going to move 1 to here, and it'll move the 2nd one to here, and then 1 on top. Then it'll move the 3rd one here, and then move the 2 back on top, which means moving 1 over, moving the 2nd, moving the 1 back. So that one's pretty quick, right? But as soon as we move to, so let's say 5 disks, right? Well, 5 is the same as moving 4 to here, moving the 5th, moving the 4 back. Well, 4 is hard. So 4 is moving 3 to here, the 4th to here, moving 3 back on top. Well, 3 is hard. So let's move 2 to here, move the 3rd one here, move the 2 back. So you're going to see that it's just this recursive step. So moving many is hard. Moving one is easy. And moving one less than many is getting us one closer to that solution. So we've moved 3, now we'll move the fourth one, and then we'll move the 3 back on top. So move 3, it's moving 2, and then moving 1. So it moves 2, then it moves the third one, and it moves the 2 back on top. To move 2, you have to move 1, move the second one, move the first one again. Now we've moved 4 from one to the other. Now we can move the fifth one, and then we'll move all 4 back on top of that one. Well, moving 4 means moving 3, and then moving the fourth, moving 3 again. Well, moving 3 means moving 2. Right? And it's just over and over and over and over again. So it's this recursive solution. So the Towers of Hanoi is actually really easy to do. I think he had his code solution. One of these websites has a code solution for it. It's like 15 lines of code. Super easy to do. But that's with recursion. Without recursion, it's much harder, because then you have to manage all of these stacks yourself. It's doable, definitely doable, and you can write it with a stack. And the iterative solution that does not use recursion is easier, or is more efficient, right? So that sort of thing. So cool. So we moved them all. Oh yeah, the book even has it. I'm sorry, that's what it is. Yep. Okay. One more recursion thing, and then we'll call it. Probably call it done. Okay. For recursion. So I'm going to look at Fibonacci. Do you guys remember Fibonacci? You might have learned about those Fibonacci numbers back in math class. The public int fib. I'm only going to say fib because I can never recall Fibonacci. You want the nth Fibonacci number, right? So remember with Fibonacci numbers. Come on, show me some numbers. Oh, math is fun. It's the same website. Look at that. Right? So it's 0 is the first one, and then 1. So technically 0 and 1 are the first two, and then every number after that is the two numbers added up before it. So what comes next is 0 plus 1. What comes next is 1 plus 1, 1 plus 2, 2 plus 3, 3 plus 5, 8 plus 5, 13 plus 8, 13 plus 21, on and on and on and on. Right? So you just keep on adding up the numbers. And Fibonacci is actually super cool. It's got this really neat, like this pattern. You find it lots of places. So the dead simple solution for this, well, what's the base case? Well, if nth is equal to 0 or nth is equal to 1, return 1. So I like skipping the 0 because I'm just lazy. I guess I'm mathematically wrong. So fine. Okay, I'll fix it. I'm sorry. Nth equals 0. Turn 0. Return 0. If nth equals 1, return 1. Okay? If it's not either of those, I'm going to return fib of nth minus 1 plus fib of nth minus 2. That's it. That is solved. Right? That is the mathematical definition of the previous two. But here's my base cases. You're either the 0th is 0 or the first is 1. That's all I know. Right? If you're not 0, you're not 1, well, let's add up the previous two. Now what's going to happen here though, right? Let's say here, I'll show you. It's fun to show you. So let's do a quick little loop here. Let's forget our Sudoku solve for a minute here. And we'll say for int nth is 1 or 0, why not? Sure. Nth is less than, I don't know, how about 40, nth plus plus. We'll print fib of nth, the nth digit of fib. Static. There we go. Or, I don't know, how about we put the nth fib, or no, should be nth plus colon, maybe, I don't know, plus, sure, why not? We'll see what we get. So we'll do the first 40 digits of Fibonacci. All right, that went relatively quick, right? That wasn't too bad. How about we go to 50? We do 50? Right, notice they're getting slower and slower and slower. Right, let's see, we might run out of room here. I think we're going to get over 2 billion soon. 400 million, 700 million, 1.1 billion. right? But 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, on and on and on. We're getting there. But it's super slow. Because what is happening here, right? Imagine this. When you say fib of, how about 7? Java is saying, okay, sure, that's fib of 6 plus fib of 5. Fib of 6 is 5 plus 4. 5 is 4 plus 3. 4 is 3 plus 2. 3 is 2 plus 1. 2 is 1 plus 0. 2 is 1 plus 0. 3 is 2 plus 1. 2 is 1 plus 0. 4 is 3 plus 2. 3 is 2 plus 1. 2 is 1 plus 0. 2 is 1 plus 0. 6 is 5 plus 4. 5 is 4 plus 3. 4 is 3 plus 2. 3 is 2 plus 1. 2 is 1 plus 0. 2 is 1 plus 0. 3 is 2 plus 1. 2 is 1 plus 0. 4 is 3 plus 2. 3 is 2 plus 1. 2 is 1 plus 0. 2 is 1 plus 0. Oh my goodness, do you see how many calls are being made? You're literally adding up the number 1, right? All of those 1 plus zeros, 1 plus zeros, 1 plus zeros, all of those are 1. So what Java did, it went through and it added 1.13 billion times just now. It added up the number 1. So it's ridiculously slow to do it that way. So this is the bad fib. I'm going to actually rename this one here to bad fib. Okay? Bad fib. Okay, so this is not ideal as a recursive solution. It's actually super easy. Iterative fib int nth. It turns out these first two are the same here. Sure. And then while then we'll have a int current nth is 2, and while current nth is less than nth, I need a previous. Int previous equals 0. Int current equals 1. And as long as we're less than the current nth, I'm going to take my int next is previous plus current. And I'll say my previous is equal to the current. And the current equals the next. Right, when I'm done, I'm going to return previous plus current. So the second fib number here, this shouldn't run at all. Right, and I'll get 0 plus 1. If I wanted the third fib number, this will run 1 time, because current, 2 is less than 3. Next will be 1 plus 0. Previous will become current was 1. Current becomes next, 1. Then the loop is done, and I'm going to return 2. Right, and on and on and on. So iterative fib here is going to run like that. Uh-oh. Nope, I broke it. Oh, current nth needs to be plus plus. There we go. That way we're not stuck in an infinite loop. Oh, yeah, we ran over our 2 billion number here. So Java starts getting stupid. So let's just stop at like 45 or so. We could use longs if we wanted, but this is fine. So see how fast that was? Right, I guess we go to 46. Yeah, like it's like that with iterative fib. Because we're adding up instead of counting up all the ones and adding up all the ones. Right? Now we could do this recursively if we wanted and not have this while loop. So sometimes with recursion, you want to have a public static int fib int nth. You want a nice pretty looking function here. And again, sure, our base cases are all the same. If not, then what we're going to do, we're going to have a private helper method, static int fib, fib helper, that takes an int nth, an int current nth, int previous, and an int current. Now this is essentially our loop here, right? We do all those same things. So if nth equals the current nth, this is our base case. We're going to return previous plus current. If we're not, right, then we need to recurse. We're going to return fib helper, given nth is the same, current nth plus 1, previous is my current, and the current is the previous plus the current. So then we can return the fib helper. So we're going to return fib helper. Nth is still the same. Current is 2. Previous is 0, and current is 1. So having all these extra variables here is not useful to someone who wants to use your method. So if you want to write a method to figure out the nth Fibonacci number, don't make them tell you the current, the previous, and the next, or current, nth, previous, and the current value. Right? Give them the same easy-looking public method here. Hey, just tell me the nth, and then use a recursive helper method here this way. So now we can still call fib, and this one should be just as fast. Again, slightly less efficient because it needs to track all of those in the loop here, because it's tracking current, nth, and previous and current. Instead of doing it in a loop here where we're saving it, it has those call stacks in the call, in the execution frames in that call stack. So this is less efficient than the iterative solution. Sure. Okay, so you know why fib is bad there then? That makes sense? Okay. Very cool. Yes, tail recursion, for sure. So tail recursion is when like the last thing that's happening is the recursive step. And if you have something that's tail recursion, where the last step is recursion, it's generally a good clue that that is really easy to turn into an actual iterative solution. Much easier. Right? Where the solution for Powers of Hanoi is not as easy. Right, because it's doing 2 different recursive steps. So you can actually look at that. The textbook has it, which is really cool. Removing end disks. He's got the solution for that one. Okay. All right. Oh my goodness, it's 7:45. Holy cow. I'm sorry, folks. That went longer than I thought. Recursion's a lot of fun, though. I'm a big fan of recursion. And it stopped again. What is going on with my internet? What is going on here? All right, I think we're back. Maybe it's just a blip. All right. Cool. All right, looking at my notifications here. I think we're good. All right. So that's recursion, right? So we also wanted to talk a little bit about generics, which we've essentially done already. So I think we did generics already. And exceptions. So we did generics. Let's talk about exceptions. So exceptions are... Oh, is that why? Is it a separate chapter? It brings it back again, doesn't it? Yeah, generics and exceptions. Okay. Yeah, it's another interlude about it. That's awesome. Sure. So the exception is the way that a class communicates that something bad happened. Right? Because you don't want to rely on system.out.println because there's no guarantee that anyone is even going to be watching for that. So when we run our class, and let's do this. So let's have some set methods here. So let's add some set methods for rectangle. Insert code, insert some setters for length and width. And then I'm actually going to call set length, because if you have the method, you don't want to do the work twice and set width. Oops, set length and set width, right? And then all of our sanity checking, all of our handling is going to happen in here. I might actually move those down a little bit here. Okay. Oops, probably not before the GIF though. So what we want to do here, we want to check. We're going to say if length is less than or equal to 0, I want to throw an exception. I want to say, no, game over. Whoever called this method did it wrong. I'm going to say throw new invalid argument. What is it? Argument. Illegal argument exception. And we'll say length cannot not be 0 or less. And what that means is whoever called that method has to catch this exception or crash. Remember back when we were getting like keyboard input, and if you try and convert something into an integer and it doesn't convert, it crashes real hard on you? We're going to do the same thing for width. And an exception is width. Causes your code to stop running. So it doesn't need an else here. Right? As soon as an exception happens, the code stops running. So there's no else block. Right? We just throw an exception and then we're done. So when we try and make a rectangle then, here in our recursion chapter, if we try and make a rectangle, sure, we'll just do this. I don't know, we'll do it up here. Let's say rectangle equals a new rectangle, and let's give it -1 and 5. Right, when I run this here, it's just going to crash hard on me. Hey, illegal argument exception. Length cannot be 0 or less. So it's up to the person calling the code to deal with it. So we could put it in a try block, right? As you see, you can try, and then you can catch possible exceptions. So we know there's a illegal argument exception. We'll just print out exception for now. It's ugly, but it'll keep it from crashing at least. So we get, hey, here's the exception, but our program didn't crash. And then inside the try block, I can do all the other things I want to do with rectangle, like rectangle.get area or something, I don't know, right? And print out. Oops. There we go. Get area. Area is colon, right? And that, no, that's not going to run because the exception happens. As soon as an exception happens, everything in that try block stops. So as soon as that exception happens, this code doesn't run, it jumps to the catch block. Okay, so you can define your own exceptions if you want. I'm quite a fan of just using the built-in ones because I think that's easier. But again, sure, sometimes it's great to have a specific exception. No big deal. Okay, you can also have a finally block if you want. So a lot of times when we use files, we'll try and close our operations in that finally block. So back when you did file operations, you had to open the file, you read or wrote to the file, and then you close the file. You might put like the closing in the finally block to make sure it gets closed properly if some exception happens. Sure. Finally blocks are great. Right, other thoughts, questions, concerns? There's not too much to it here, but again, the idea is that your class is responsible for maintaining its integrity. So exceptions are the only way the class communicates with the person calling it that something bad happened. You can't just print something to console. Please don't ever use print lines for error messages, right? Inside of a class, right? Inside your method with main, sure, go for it, because that's, if someone's running it from main, they're expecting a console application, and they're probably looking at it. But when you write a class, you don't know if it's going to be used in the console, you don't know if it's going to be used in a GUI application, in a web application, in a mobile application. Right? The idea is our classes are portable and reusable, so this is how our class communicates with the caller. That's the big piece there with exceptions. Okay, I'm sorry, we did not take a break. I'm feeling terrible. How are you folks doing? You hanging in there? Or did I lose you all with Sudoku? All right, I'm glad you survived, Dusty. Good to know. You're hanging in there. All right, well, the good news is that's all I've got. So I'll post the quiz later tonight about recursion, exceptions. I don't think there's anything we need to talk about for generics. We did generics, right, when we started talking about those stacks. Like back when we started doing stacks, they're like, oh, here's a T. So yeah, do read the interlude, right? Definitely worth reading there. Pain, Professor Burp, sorry. Yes, so the current quiz here, right, from last week is due tonight, 11:59 p.m. So chapters 5 and 6 and interlude 7. It just got long to put the name in there. Don't forget to get that one in by 11:59 p.m. tonight. I'll post this week's quiz on recursion, generics, exceptions. Excuse me, I'll post that one later. And then we'll have, again, a week to do that. Next week, the war project is due. Got to keep these things straight in my head. We are just flying by. So we're officially a third of the way through the class, 33% of the way through. And, you know, 1 week is a midterm and 1 week is final presentations. So in terms of content, we're almost halfway through the content, right? In terms of things that I'm going to be talking to you about and showing you things, right? Because we only have 13 weeks of me talking at you, right? If you take out the midterm and the final project, we're almost half. Right, so I'll talk 1, 2, 3, 4, 5, 6, 7 more nights. The midterm is July 14th. Yep, the 10th week. After we finish the individual projects, and then we'll get into the final project and wrap up. Sort of work with the flow. Okay, so 5 weeks of me talking at you. We've got 7 left. We got a midterm. We have final project work time, final project presentations over Zoom coming up. Again, keep those in your calendar. And we are just cruising. Next week, I'll solve Project 2, the little war simulator. We'll talk about sorting, and then we'll talk about the next individual project. We'll do queues, DQs or decks, priority queues, lists, iterators, sorted lists, the midterm, searching, dictionaries, hashing, more hashing trees, binary search trees, heaps, bound search trees, graphs, and we're done with content. So this semester just flies at you. All right, so let's go find somebody to raid. I'll be around tonight. I have office hours from 10 to 11 tonight. If you folks have questions about the project, please chat with me then, or next week Monday, next week Wednesday during the day, 3 to 4:30 p.m., Monday 10 to 11, or Mondays and Wednesdays 3 to 4:30 and 10 to 11 p.m. Okay. All right, so let's head on over. And we'll be talking about the trees the week after, so possibly I'm still hashing out exactly what we're going to have in the final there. We'll go head over to my friend Mr. Noir's channel if you're curious. We'll have some fun. Folks, take care, and I will see you around. All right, folks, let me go to this ending screen. Look at that. And take care. I'll see you there.